Here's another one of those basic differentiation facts that takes a little bit of, rather than just accept it, you ought to spend a little bit of time and think about where it comes from. And it involves a little bit of tricky mathematical process that is not all that uncommon in mathematics, but may tend to make your head hurt for a while. So the fact is that the derivative of e to the x is in fact itself. It is e to the x. That's the one function whose derivative function is exactly the same as the function itself. So you can just accept that and be able to calculate, but you should look deeper into the mathematics, because this whole mathematical reasoning thing is part of what is the important takeaway from a calculus course, rather than just memorization and calculation. So we're going to beat around the bush a little bit here by considering the derivative with respect to x of a general exponential. A to the x. A could be 2, A could be 3, A could be e, A could be pi to the x. It's just some number raised to the x. If you graph that, you will see an exponential curve. It's just each one's a little bit different exponential curve depending upon the value of a. So if we were to try to address that problem, a more general problem, the derivative of a to the x, how would we do that? Again, we're at square one. We only have one tool in our arsenal right now, and that is the definition of derivative. So here we go with applying the definition of derivative to a to the x. That would be f of x plus h, which in this case is a of x plus h, minus f of x, which in this case is a of x, all over h, the limit as h goes to 0. That would be the derivative of a to the x. We're not going to be able at this point to come up with the derivative of a to the x, but we're going to be able to leverage this reasoning into showing that there is a function whose derivative is itself, and in fact we're going to define that value of a for which that is true to be e to the x, and then later on we'll show it's the same old e that you are familiar with. And if you can duplicate this at some point in here before the next test, you'll get some points for spending some time on learning how to think about this kind of process. Okay, so here we go. Here's the definition, limit definition of the derivative of a to the x, and now it's algebra time. If this was the sine of x, it would be trig time, but it's algebra time. Oh look, there's an a to the x in each of these. A to the x plus h is a to the x times a to the h, and the a to the x cancels, will factor out of both of those terms, leaving a to the x times the quantity a to the h minus 1 all over h. And you can put it back in there and see that that's so. And then what you should notice here is that a to the x has nothing to do with h, therefore that a to the x can be pulled out in front of the limit. So let's take a look at doing that. We pull that out in front of the limit, and what we see here is that when we pull it out in front of the limit, the derivative of a to the x is actually just a to the x times some thing here that turns out to be just some number. If you take 2 and take the limit as of 2 to the h minus 1 over h as h goes to 0, you can put that in your calculator and try it at h is 0.1, 0.01, 0.001. You would discover that it's just, it converges to a number. It would appear to converge to a number. This is not a formal proof again. This is just kind of a justification. You can look for a formal proof in advanced calculus. Okay, so what we take away from this process here is the derivative of a to the x is a to the x times something, and the thing is whatever this limit happens to be. So if we pick a as 2, we get derivative of 2 to the x is 2 to the x times some number that is the number that is the limit for 2 when a is 2, and that turns out to be some particular value. So hold on to your hats, this is the tricky part. If a is 2, you can take 2 to the h minus 1 over h and let h go to 0.1, 0.01, 0.001, and you will see that it appears to converge to a number that is less than 1. If in fact you take a to be 3, that limit 3 to the h minus 1 over h, and you put in 0.1, 0.01, 0.001, it appears to converge to a number that is somewhat larger than 1, which leads one to believe that there must be some number between 2 and 3 for which it is exactly 1. And if that number is used as the base, then this blob here, which is the limit as h goes to 0 of a to the h minus 1 over h, turns into 1. And if that turns into 1, that's the point at which the derivative of a to the x is equal to a to the x, assuming that you've picked the right a, the one that's somewhere between 2 and 3. If you will remember, e is such a number. So in a somewhat interesting way that mathematicians have of doing such things, since there is an a between 2 and 3 for which that limit is 1, we're simply going to say let's call that number between 2 and 3 for which this limit is 1 and gives us the fact that a to the x derivative is equal to a to the x, and we'll just define that number a that makes that happen as e. And it turns out that in that case we have the fact that the derivative of e to the x is e to the x. If you want a graphical proof of that, you could define the function e to the x and then graph e to the x and the derivative of e to the x in Mathematica, and you would find out that they are in fact appear to be the same exact curve.